Hello. So, as my title card here implies, I'm going to give you a brief lesson with some examples of why polarity and hydrogen bonds make a difference in the properties of different substances. All right. Before we get started, let's review a couple of things. First of all, we're going to be looking at organic compounds that contain carbon, hydrogen, and sometimes oxygen. And carbon can make 4 covalent bonds usually. Oxygen usually makes 2, and hydrogen always makes 1 covalent bond. So you'll see here that if you pay attention and look at all of the carbons and oxygens, you'll see that they only have 4 or 2 bonds connected to them. Also, let's review about the polarity of bonds between these 3 elements. A carbon-hydrogen bond is considered nonpolar. The difference in electronegativity is not great enough for it to be considered polar. A carbon-oxygen bond, however, is polar, and an oxygen-hydrogen bond is even more polar than a carbon-oxygen bond. And it's bonds between the polar bonds between hydrogen and nitrogen, oxygen, and fluorine that are so polar that they allow hydrogen bonding to occur. All right, so what I'm going to do is show you 4 different compounds and how polarity and hydrogen bonding affects their properties. The first one I'm going to show you is propane, and just as a side note, the prefix prop in organic chemistry means that you're dealing with something that has 3 carbons in it. So all of these things are going to have prop in the name because they all are 3 carbon compounds. All right, propane's formula is C3H8, and here is a Lewis structure for it. Pretty simple. All carbon-hydrogen bonds, all those bonds are nonpolar. Since they're nonpolar, they don't have any charges, even partial charges, so there is no electrostatic attraction for propane and other molecules of the same compound. So, as you probably have experienced in your own life, propane is a gas, it's flammable, and it's a gas because it won't stick to itself. It's not a super light molecule compared to, say, oxygen, but it still is not very heavy, and if it won't stick to itself, then it will be a gas. Our next example is going to be acetone. I just want to point out that there are a lot of the names I'm going to be using are common names. There are standard names, international standard names, and that one would be propanone for this, so we see the prop prefix come up again. So also this is a 3 carbon compound like we were seeing before. The difference is that there's an oxygen in here. It's a double bonded oxygen. So in the middle. This makes the acetone molecule just slightly polar because the oxygen carbon bond is a polar bond, and so the oxygen is partially negative and the carbon is partially positive. This means that the acetone molecules will stick to each other a little bit, and that makes acetone a liquid instead of a gas. You are probably familiar with acetone most commonly as nail polish remover. It's got a sort of alcohol-y smell, and it is a liquid. It will also mix with water as well as alcohol. All right, next one is going to be isopropanol. The international name is 2-propanol. Now we're getting into formulas that are complicated enough that sometimes the formula is written in a way to show the structure of the compound, and so these are called structural formulas. So here are 2 different formats for the same formula for this molecule. Again, it's a 3 carbon compound. And instead of having a double bonded oxygen in the center here, we have an oxygen bonded to a hydrogen. This is also a polar bond, as you know. So we have a partially negative charge on the oxygen and a partial positive charge on the hydrogen. This means that if you were to mix this alcohol with water, the opposite partial charges on the water would be attracted to the isopropanol and would mix, and so it can dissolve, they can dissolve in each other by forming hydrogen bonds. So if you think about alcohol, this actually, isopropanol is commonly known as rubbing alcohol. So you've probably encountered it too. It is a liquid, but it has it's not nearly as wet as water. It evaporates really quickly. You get that cooling feeling on your skin when you have it on your skin because it doesn't stick to itself quite as well as water does. All right, next up, we have propylene glycol. Propylene glycol is very similar in structure to isopropanol. The only difference is that there are two oxygen-hydrogen sets on this 3-carbon molecule instead of one. This means it's got double the bonding power that isopropanol does, and so it sticks to itself much better. Instead of being a thin liquid, it's actually a fairly viscous liquid. It's like thin maple syrup in consistency. Propylene glycol will attract water because of those polar groups, and it's used to keep things moist, both food and non-food products. A sort of infamous example of how it's used a lot nowadays is that it's the basis for vape liquid. All right. Last one we have is glycerol, or propane 1,2,3-triol. The "all" here, as you might have figured out by now, means alcohol, and that the thing that makes these alcohols is having an oxygen-hydrogen attached to the carbons. So isopropanol had one oxygen-hydrogen, propylene glycol had two, glycerol has three. So as you might expect, having one more oxygen-hydrogen group on this makes it even more polar than the previous two, and so it sticks to itself even better. And glycerol is very viscous, very thick. It's more like honey in consistency, and it is even more moisturizing, and therefore it gets used in all sorts of different cosmetic products. Lotions, oftentimes soaps and shampoos. It has many uses because of that. So there you have it. The more polar bonding a molecule can make, the more it can stick to itself, and the more it can mix with water. So if it's not polar at all, we have something that's a gas like propane, all the way over to something that's viscous and syrupy like glycerin. All these things are based on 3 carbons. The only difference is how many polar bonds we've added to them. All right, I hope that helps give you a feeling for how polarity and polar bonds and hydrogen bonding affect the properties of these compounds.